Welcome to the second video lessons of basis and dimension of vector space under PMAT 21553. So in this lesson we will introduce the dimension of a vector space and discuss how to form a basis of a vector space. First we will go through the definition of a dimension of a vector space. If a vector space V has a basis consisting in vectors, then the number n is called the dimension of V, and it is denoted by dimension of V. Dimension of V, dim V is equal to n. If V consists of zero vector alone, the dimension of V is defined as 0. So, if the dimension of basis of a vector space contains in vectors, you may remember in the previous lesson we say that any basis of a vector space contains the same number of vectors. So therefore any basis of V contains only n number of vectors. So in this case we call dimension of V is equal to n. So we denote it by writing dim V is equal to n. So if V contains only a zero vector, so only a zero vector, so we do not call it, it contains only one element, zero vector. In this case, we consider the dimension of V is equal to 0. Dimension of V is equal to 0. So the idea, number of elements in the basis is called the dimension of the vector space. Now look at this example. You may remember we introduced the standard basis. In Rn, we consider the standard basis E1, E2, E3, En, where in the ith positions it contains 1 and any other positions of Ei, all components are 0. For example, E1, the first component is 1, other components are 0. E2, the second component is 1, all other components are 0. En should be 0, so typing mistake. All components other than nth component are zeros. So in this case, in the basis, it contains n element, so the dimension is equal to n. The next one, if you take the set of polynomial of degree n, so it can be written as, you may remember, a naught e1 x plus e2 x squared and so on, an xn. So you need 1 x squared x3 and so on xn to write down the any members of the set of polynomial of degree n. So it contains n plus 1 elements. So therefore the degree is n plus 1. The dimension is n plus 1. Okay. So if you have a set of matrices of m cross n with the standard operations, matrix operation, matrix addition and matrix multiplication, it forms a vector space. So in this case, any elements of the form E11, E12, EMN, so they are missing, so the last one should be EMN. So anyone Eij in the ith row and jth column, it position it contains 1. Any other components and any other elements are 0. For example, if you have if 2 m22, so that means matrices containing 2 by 2, it positions 1 0 So this is E11, E12. So 0, 1, 0, 0. E21 is 0, 0, 1, 0. E22 is 0, 0, 0, 1. So this matrices E11, E12, E22, E21, E22 will form a basis for M22, and it contains 4 elements, 2 by 2, 2 onto 2. So the dimension is 4. So in general, if Mn is the set of matrices M cross N, standard basis can be written in this form, and it contains M times N elements. So the dimension of this vector space is Mn. For example, R4 standard basis, you may remember E1, E2, E3, E4. So it contains 4 elements. So therefore dimension is 4. P4, the vector space basis 1 x, x squared, x cubed, and x4. So it contains 5 elements in the basis. So therefore dimension of P4 is 5. Dimension of M32 I have explained in the previous example. So the dimension is 3 into 2, it is 6. Now just consider this example. Determine the dimension of each subbase of R3. It is in the form of DCD minus DC, where C and D are real numbers. The second subbase is 2BB, 2BB0, where B is also a real number. We will take one by one. First one, subbase of the form DC minus DC. You can split these into two vectors, C terms and D terms, and take in C out of the component. So this you will get one vector and the other vector. So therefore you can see that the subbase is spanned by these two vectors 0, 1, 1 and 1 minus 1, 0. You can clearly take that C1 times 0, 1, 1 plus C2 1 minus 1, 0 equal to 0. Then you will see that you can compute it. C1 is equal to 0 and C2 is equal to 0. Therefore, this set is linearly independent. So, therefore, the set is linearly independent, and it spans the subbase W. So, therefore, this S is a basis for the subbase W. So, the dimension of W is equal to 2 because S contains only two linearly independent variables. We can show that S is linearly independent, that we have already done. Hence, S is the basis for W. The dimension of W is 2. Now, the second part B, it has the subbase 2BB0. So taking B out, you can get only one vector. So therefore, this 210 will span the subbase W. Sorry, W is spanned by the set 210. So a singleton set is linearly independent if the vector space contain only one element. So it is always linearly independent. So yeah, therefore the dimension of W is equal to 1. So it is a basis for W and it contains only one element. So therefore dimension of W is equal to 1. Now we go to the next theorem. Basis test in an n-dimensional space. So test for a basis. So how to identify the basis? So the theorem says, suppose that V is a vector space with the dimension of V is equal to n. Then the first part says that if S containing n elements V1, V2, Vn is linearly independent, then span S is equal to V and S is a basis. So that means if we have a vector space with the dimension is n and it contains linearly independent set V containing n elements. So this is S, it's a subset of the vector space. It says if S is linearly independent. So this implies S persists that span is equal to V and S is a basis for V. S is a basis for V. So if we can start with S is linearly independent and show that expansion of S is equal to V, the vector space, and S is a basis for the V. And the second part, it says that if S span S, if S is this one, and if span S is equal to V, then S is linearly independent and it is a basis. So it says that in the second part, this sec vector, if span S is equal to V, then S is linearly independent and S is a basis. So you can use this theorem if you can get a linearly independent set of containing n vectors in a vector space with the dimension n, you can immediately claim that it is a basis. And conversely, if uh, a subset is containing n elements spans V, then you can say that it is linearly independent and also it is a basis. So let's see how to prove this theorem. So the first part says that we want to say that if S is linearly independent, then span S is equal to V. So that means we have to prove that S spans V and S is a basis. So suppose that S is linearly independent and just take any vector V, be any vector in V. So we want to prove that if uh, V is in S, so that means V is in spans of S. So that means if V is in spans of if V is in spans of S, we can clearly see that no. But we want to say that if V belongs to S, if V belongs to X, that means V is in spans of A, because we can write as V as 1 times V. All other components are V2, V1, other components are 0. So that means if V contain in S, V can be written uh, as a linear combination of vectors of S. So that means V belongs to the spans of S. So suppose that V does not belong to the S. So that means V does not belongs to S. So we are going to prove that any set containing V is linearly dependent. So since dimension of n, dimension of V is equal to n, any set containing more than n elements is always linearly dependent In the previous lessons, we have discussed such a theorem. Now, so therefore, if we take this set, it contains n plus 1 elements. So that means more than n elements. So it is linearly dependent. So linearly dependent means if we take a linear combination of this set, C1 V1, C2 V2, C3 V3 plus Cn Vn plus Cn plus 1 V is equal to 0, then at least one coefficient should be not equal to 0. So that means in this linear combination, at least one component, one coefficient is not equal to 0. Suppose that Cn plus 1 is equal to 0. In this case, this term disappear. Then you have C1 V1, C2 V2, C3 V3 plus Cn Vn is equal to 0. But you know that V1, V2, V3, Vn, they are linearly independent set. If they are linearly independent set and it is the linear combination is equal to 0, so in this case all the coefficients should be equal to 0. So that means if Cn1 plus is equal to 0, all coefficients C1, C2, Cn plus, all they are equal to 0. But it is not possible because this set is linearly dependent. So if all coefficients are 0, that means it is a linearly independent set. But we know that the set contains V, V1, V2 and Vn, they are linearly independent. So therefore our assumption Cn plus 1 is equal to 0 is wrong. So therefore it should be not equal to 0. Cn plus 1 is not equal to 0. Now since Cn plus 1 is not equal to 0, we can take this term, all the other terms to the other side and divide by Cn plus 1. So we can be expressed in terms of V1, V2, V3 and Vn. If we can be expressed in terms of V1, V2, Vn, so that means so we have taken any vector, arbitrary vector V in S. So we can be written as a linear combination of Vi. Let's say I will take Ki for this representation. So we can be written as a vectors of V. So that means S spans V. S spans V because any vector in V can be written as a linear combination of members of S. So conversely, suppose that S spans V. Now what in the previous case? So what we have seen that S spans V. Now S is a linearly independent set and it spans V. You know that by the definition of basis, if there exists a linearly independent subset and if the subset spans the vector space V, so that means S is a basis for V. So that means what we have proved that if the dimension of vector space V is equal to n, any vector, any subset containing n linearly independent vectors, so linearly independent, so this implies S is a basis. S is a basis. So the idea, if the dimension of the vector space is n, any subset containing n linearly independent vectors will form a basis for the vector space V. Now the converse, suppose that S spans V, S spans V. So in this case, to show that, so we have to prove that if S spans V, S is linearly independent, and since it is S spans V and S is linearly independent, it is a basis. To prove that S is linearly independent, we will use the method of contradiction. So that means we assume that S is linearly dependent. S is linearly dependent. So, if S is linearly dependent, at least one vector of S can be written as a linear combination of the other vector. So that means V1, V2, Vn, it contains n vectors. Suppose there is a vector, let's say Vk. In this case, Vk can be written as a linear combination of other vectors. So I is equal to 1 to n, Ci Vi. So I is not equal to k. So that means we can eliminate from this set, we can eliminate this Vk because it is a linear combination of other vectors. So then new set will contain only V1 without Vk minus 1, Vk plus 1 and Vn. So it contains only n minus 1 element. So without changing the spans, um, we can remove one element from the set if it is linearly independent. We can remove one element from the set and it will contain only n minus 1 element. But we continue this process until we arrive linearly independent set. So we start with the set V1, V2, Vn and remove one element. So it contains n element. Remove if it is not linearly independent, we remove one element because one element can be written as in terms of the other element. So then it will contain some certain vectors, contains only n minus 1. If this is also not linearly independent, we can remove one more element to get another set containing n minus 2. So until we get a linearly independent set. Now what we have said that finally, suppose we have some certain vectors containing m vectors, m is less than n. So this set is linearly independent and it spans the vector space V. So this will form a basis. So the dimension of this basis, it contains only n m elements. Dimension of V will in this case will be equal to m, which is less than n, but we are given that the dimension of the vector space is n. So if we assume that S is linearly independent, we will end up with the contradictory results. The dimension of V is not equal to n, it is less than n. So this will give you a contradiction. So that means our assumption is wrong. So what is our assumption is S is linearly dependent. So that means our assumption is wrong means S is linearly independent. So now S is linearly independent, S spans V. So therefore S is the basis by the definition. If S is linearly independent and if it spans the vector space, it is a basis. Okay. So how we can use this theorem to do some to work out with some example. So we want to determine whether this B is a basis for R3. Now you remember in the standard basis of R3 contain 3 elements. So therefore the dimension of R3 is equal to 3. So any vector containing 3 linearly independent vectors will form a basis for R3. So what we have to say, if we want to check whether this B is a basis, since it contains three vectors, only three vectors, if this is linearly independent, then it will form a basis for R3. All we have to check whether D is linearly independent. Since the dimension of R3 is equal to 3, B contains three vectors. So if B is linearly independent, then it is a basis. So we want to consider that whether this B is linearly independent. You may remember in the previous course material we introduced, if a matrix can be formed from the vectors v1, v2, v3. So the as column v1, v2, v3. If this matrix is the determinant of this matrix is not equal to 0, so that means the vectors v1, v2, v3 are linearly independent. Now you can calculate the determinant of v very simply. So it is the value v is 1. So you get only for this 1 into 1, 1. So 1 times 1 minus 0 plus minus 0 times something. We don't need this. So 1 times 0 minus 0. So it is equal to 1. So the determinant of A is equal to 1, not equal to 0. So that means all the vectors in the column of A are linearly independent. So that means B is linearly independent. So B contains three elements and it is a linearly independent set. So the dimension of R3 is 3. Any subset of R3 containing three elements will form a basis for R3. So therefore B is a basis for R3. Now suppose we have given a set, collection of sets. So we want to find a basis for spans S where S is given by this. So what we can do? So in the spans of S, we want to find a basis for spans S. Now you know that any spans S mean if any vector containing in the expansion mean V is a linear combination. V is a linear combination of this set. Now to find out a basis, you need to take linearly independent set of this vector, linearly independent set from this S. To do that, just consider we select a linearly independent vectors of S to form a basis for spans S. Now just consider a linear combination is equal to 0. So from this relationship, we want to find out a linearly independent set from V1, V2, V3, V4, V5. Now we substitute V1, V2, V3, V4 and it will give you a system of linear equation. So augmented matrix for the system of linear equation will take in this form. So you can see that as usually you can take first component, second component and third component. So therefore it will contain 5 variables and 3 equations. So the associated augmented matrix for this system of linear equation is like this. Now you can reduce this augmented matrix into row echelon form. So I am not going to discuss how to find the row echelon form. These things we have discussed in the first year in matrix algebra course. So then that is the reduced row echelon form of the augmented matrix. So you can write down the you can see that it contains it has number of variables are 5 is 5, but it contains only 3 non-zero rows. So therefore it has infinitely many solutions. So this is the corresponding associated equivalent system. So you have to assign some parameters because it has n is equal to 5 and r is equal to 2 number of non-zeros. So if you need 5 minus 3, it should be 3. 5 minus 3 two parameters to describe the solutions. Now we assign C1, C5 and C4 as T, where T and S the parameters. So then you can calculate C3, C2 and C1 in terms of T and S. Then you can assign these values into the previous equation. C1 is equal to minus S, C2 is equal to minus T minus S, C3 is equal to minus T, C4 is S, C5 is T. Now, if you set T is equal to 0 in this equation and S equal 1, you get V5, V4 is equal to V1 plus V2. Setting T1 is equal to 1 and S equal 0, we get V5 is equal to V2 plus V3. So V4 can be written in terms of V1 and V2. V5 also can be written as in terms of V2 and V3. So V1, V2, so V3, V4 can be written as V1 plus V2. V5 can be written as V2 plus V3. So therefore, we can see any set of expansion this contains V1, V2 and V3, because any other set is again a combination of V2 and V3 or V1 and V2. So therefore, this will be linearly independent set of the set V1, V2, V3, V5. So hence linearly independent set containing vectors V1, V2, V3, and it forms a basis for span sets. So what we have done, since we get V1, V2, V3, V4, V5, so to find out the basis for this spans of S, we select the linearly independent set from V1, V2, V3, V4, V5, taking a linear combination into 0. So, but alternatively, we can use some easier method to find out the linearly independent vectors from a given set. So, we can assemble all the vectors of X in a matrix in a column as a column. So, V1 1 0, V2 1 0 1, V3 2 1 2, V4 2 1 1, V5 3 1 3. So, what we have done, so we have the vectors V1, V2, V3, V4, V5. We assemble all these vectors in a column of a matrix A. So now having this matrix A, we reduce A into its row echelon form. So A, it can be using elementary row operations, it can be reduced into its row echelon form. Now once you have the row echelon form, you select the columns corresponding to the leading one. So that means in this one, you can see in each row you select the uh, column which has leading one. So here is leading one for first row. For the second row, the leading one is this one. For the third row, the leading one is here. Now you take V1, V2 and V3. So they are the linearly independent set of this collection. So therefore, they are linearly independent. So what we have done, convert the matrix into its row echelon form and find out the columns which contains leading one of each row. So then set will be linearly independent. It form a basis for spans of S. Now we can summarize this procedure to say how to find the basis for the spans of a set of vector space vectors. So if you are given a set of set of vectors v1 v2 vn s, so we want to find the basis for spans of s. So the first step is form a matrix whose the column vectors are v1 v2 vn. So you assemble all v1 v2 vn in a column, so it will form a matrix. So reduce the matrix into row echelon form, and the vectors from S that correspond in the column of reduced matrix with the leading one are is the basis for S. So you select the corresponding column vectors which has each row the leading coefficients 1. So then this will form a basis for the spans S. Maybe we can see one more example to understand it very clearly. Suppose we are given a set S, so we want to find the basis for spans of S. So we assemble the columns of the vectors S in a matrix. So you can see here. So the first column, second column, third column, fourth column, and fifth column. Now you can see we have assembled the vectors of X in a column of a matrix A. Column of a matrix A. Now we take this matrix and convert it into its row echelon form using the row operations. So reduce row echelon form. So it will give this reduced row echelon form. Then we collect the column which contains leading one of each row. So for the first row, the leading one is here. So it is in the first column, V1. For the second row, leading one is here. So it is in V2. For V3, the next leading one is here. It is in the third one. So it should be fourth column, fourth one. Now, V1, V2, V4. So V1, V2, V4 will form a basis. They are the linearly independent set of the collection, and it will form a basis for the spans of S. Basis for span S is collect V1, V2, and V4. So this will form a basis for span S. So the idea is you assemble all the vectors in a matrix as a column vectors and convert this into reduce this into its row echelon form and collect the columns which has each row the leading one. So then it will they will be linearly independent and will form a basis for spans S. Now we move to the another theorem. Suppose this is a very important theorem in vector space because it can be used to extend a given linearly independent set into a basis. So we will discuss it later. The theorem says, suppose that S v1, v2, vn is linearly independent subset of a vector v. We don't know the dimension of vector space v. If v is a vector in v that is not in spans S, then T is linearly independent. So what it says that if we have a vector space v and containing the v1, v2, vn, they are linearly independent. This is the set S. They are linearly independent. If V is not spans of S, if V is not span set S, then when you add this V into another set, so this is T is linearly independent. So if V1, V2, Vn is linearly independent, and if we have another set which does not belongs to the spans of S, then if you add this V into S, then it will be another collection of vectors. It is also linearly independent. So how we can prove this? So we know we want to prove that T, this set, is linearly independent. So we know that V does not belongs to span S, and S is linearly independent. So that's what we have got. So V does not belong to spans of S. S is linearly independent. So we want to prove that T is uh, linearly independent. Now we consider to show that the set of vectors in T linearly independent. So you take a linear combination is equal to 0. Now if C1 is not equal to 0, if this is not equal to 0, so that means we can take this term to the other side and divide by Cn plus 1, because Cn plus 1 is not equal to 0. Then V can be written as this. V is equal to this. But it should be C1. But you know that so in this case V can be written as a linear combination of V1, V2, V3, Vn. So this implies V belongs to spans S, because V can be written in terms of V1, V2, Vn. But this is contradicts the fact that V does not belongs to spans of S. So that means our assumption is wrong. Cn plus 1 not equal 0, assumption is wrong. So then we got Cn plus 1 is equal to 0. So this term is equal to 0. This term is equal to 0. Now V1, V2, Vn, they are linearly independent set. If this is equal to 0, so that means all the coefficients are equal to 0. C1, C2, Cn, all the coefficients are equal to 0. All the coefficients are equal to 0 because V1, V2, Vn are equal to 0. So what we have proved that C1, C2, Cn, all they are equal to 0. Cn plus 1 is also equal to 0. So that means this set T is uh, linearly independent. Sorry. Now, uh, now what we have seen, if V1, V2, Vn is linearly independent, and if we have any set which does not belongs to spans of S, then we can form another linearly independent set V1, V2, Vn containing these new points V. So starting with this, we can form another linearly independent set. So the above theorem can be used to form a basis for a vector space starting with the linearly independent set, with the linearly independent subset of V. Now we can go to the next theorem, that is known as extension theorem. As I told earlier, this is very important theorem, because now let's see what is the theorem says. Let S is V1, V2, Vr be a linearly independent set of vectors in an n-dimensional vector space V, with R is less than N. Then S can be expanded to a basis for V. So that is, there is a vector space now containing, there is a set VR plus 1, VR plus 2 and VR. So this new set collection VR plus 1, VR2, Vn, when you add this set into the original one, S, it will form a basis. So the idea again, so V1, V2, VR, it is linearly independent. R is less than N, linearly independent. Now this can be extended adding another vectors VR plus 1, VR2, N. Why it is? Because we know that dimension of N, dimension of the vector space is N. Now, if this contains R and if we have N linearly independent vectors, a vectors containing N vectors, it is a basis for the vector space. So therefore, since this contains R linearly independent vectors, we need another N minus R vectors to be added to this set to form a basis. So therefore, we start V1, V2, Vr and add another N minus R vectors. So we have R vectors here and this will be N minus R vectors. Altogether it contains N vectors linearly independent. So therefore this will form a basis. That's the idea. Let's see how to prove that. Suppose that V1, V2, Vr is linearly independent. Now we take any vector Vr plus 1 from the vector space V, but it does not belongs to Vr plus 1, does not belongs to span S. So as for the previous theorem, when you add this Vr1 into this set, it will be a linearly independent set. So we denote it by S1. Denote it by S1. Now what we have, S1 together V1, V2, Vr and with the Vr1 plus, which does not belongs to the expansion of S, is linearly independent. Now we have S1, V1, V2, Vr, Vr plus 1. It is linearly independent set. We consider another set Vr2 in the vector space V, which does not belong to the spans of S1. And then from the previous theorem, you can claim this, adding this new vector into S1, it is also linearly independent. It is also linearly independent. So you start with S and form a vector x1 linearly independent. Starting with x1, you form another set of vector s2. Now we can continue this process. So here we have r. Now we add one more vector r plus 1. Here we have one more vector r plus 2, contain r plus 2. So likewise, you can consider the final vector n minus, it should be n minus r, yes, and it contains n vectors. So you can find a set containing n vectors. So we can extend this process until we get linearly independent set. So this is what I denote in x minus r. So it contains, here you have n minus r elements, here you have r elements. So this is altogether it contains n linearly independent vectors. Since this contains n linearly independent vectors, it is a basis because the dimension of V is equal to 1. Since the dimension of V is equal to 1, so this will form a basis for V. So starting with the vectors V1, V2, Vr, we can extend this. If this is linearly independent, we can extend this into another set which is linearly independent and containing n elements, and it will form a basis. So how we can use the previous theorem to form a basis for R4? Suppose we are given two vectors v1 and v2. You can clearly see that it is linearly independent and it is given. Now what we can do, since the dimension of R4 is 4, so we want to find out a basis of 4 vectors containing v1 and v2. Now, so to do that, we take a set S containing v1 and v2. Since we do not have any other idea about the other vectors, we include standard basis of R4, E1, E2, E3, E4. Now it contains 6 vectors, but we need only 4 vectors to form a basis. Okay, since S contains more than 4 vectors, it is linearly dependent. So we want to find out the linearly independent vectors of S. So we can do it as follows. Now we form a column vectors into a column v1, v2. So e1, e2, e3, e4. So that's how we form the matrix. Now you convert it into reduced row echelon form. Once you convert it into a reduced row echelon form, then you take the columns which has lead in 1. So choose the corresponding to column vectors which has lead in 1 in row echelon form. So these are the lead in 1. So it has v1, v2, e1 and e2, e3, e4. Now you can see v1, v2, e1, e4 will form a basis for R4. Basis for R4 is v1, v2, e1, e4. Okay, that's how we extend to find out the basis for R4. So you start with v1 and v2 at standard basis e1, e2, e3, e4, and then starting with this, you select the linearly independent set from this. We assemble them in a column vectors and convert it into row echelon form and find out the columns where it has lead in 1. Okay, so what we have discussed in these lessons, the definition of a dimension of vector space and what are the properties of basis and the relationship basis and linearly independence. If you have a linearly independent set, how we can form a basis for starting with this linearly independent set. So extending a linearly independent set into a basis of a vector space. For further details, you can go through the these recommended textbook, Linear Algebra by Ron Larson, Introduction to Linear Algebra by James De France, and Elementary Linear Algebra, an application version of Howard, Anton, and et al. So thank you so much for joining with us. So I will come up with another video lesson for the column space and row space of a vector space, rank of a matrix, and other things. Thank you so much.